The flight computer you can also use for calculating gallons. The outside scale of the flight computer also represents your fuel, or the amount of gallons of fuel that you're using. Suppose that the FAA said to you that you have consumed 10 gallons of fuel in 1 hour. You've consumed 10 gallons of fuel in 1 hour, and you want to know how much fuel you would use in 2 hours. 10 gallons in 1 hour, how much fuel are you going to be using in 2 hours? Let's take a look at the flight computer. On the flight computer, you've got gallons on the outer scale, 10 gallons, and we used 10 gallons in 1 hour. 1 hour is how many minutes? 60 minutes. So move the inner scale around until the 60 on the inside is next to 10 on the outside. You're setting up a ratio of how many gallons you're using, how fast you're using fuel in so much time. So we've got 10 gallons of fuel in 1 hour and 60 minutes, and 1 hour, which is 60 minutes. And the question is, how much fuel will we use in 2 hours? So we simply look around the inside scale of the flight computer until we find 2 hours, which is 120 minutes. And the 12 on the minute scale will represent here 120 minutes. And notice on the far inner scale, we've got the 2 on there for 2 hours. Okay, if you're going to burn fuel for 2 hours and the rate you're burning it is 10 gallons an hour, on the outside scale of the flight computer, it will tell you how many gallons you're going to have used and how many gallons will you have used. 20 gallons in 2 hours. 20 gallons in 2 hours. Okay, let's assume the same rate of fuel consumption, still burning it at 10 gallons an hour. How much fuel would you use in 2.5 hours? You simply look further around the inner scale until you find 150 minutes. 15 on the minute scale, representing 150 minutes, which is 2 hours and 30 minutes. And you'll find that 2 hours and 30 minutes, 2.5 hours, on the far inner scale. And on the outside scale of the flight computer, you'll find how many gallons you'll use in 2.5 hours. And how many gallons is that? You got it, 25 gallons. 25 gallons you're going to have used. Now, still burning fuel at the same rate, how long would it take you to burn 7 gallons? Well, the gallons themselves you always find on which scale? The outside scale, the outer scale. So you look around the outer scale until you find 7 gallons. Now, you don't have a 7 on the outside scale, so we're going to use the 70 instead to represent 7 gallons. 7 gallons, and on the inner scale it will tell you how many minutes it will take to burn 7 gallons. And here's 40, 41, 42 minutes. It's going to take us right at 42 minutes to use those 7 gallons. Now, let's assume that the FAA came along and said to you on the test that you used 15 gallons of fuel in 45 minutes. 15 gallons of fuel in 45 minutes, and what they want to know is how much fuel are you burning per hour. Okay, you go to the circular slide rule side of the flight computer, and what is the first thing you always set in? How fast? How fast, in this case, are you using fuel? You say, I don't know how fast I'm using fuel. Sure you do. You know you used 15 gallons in 45 minutes. That's how fast you're using fuel. And you set that ratio in on the flight computer. Gallons are on the outer scale. So you look on the outside scale until you find the 15 for the 15 gallons that you're using. You used 15 gallons, and you used 15 gallons in 45 minutes. So you move the inner scale around until you find 45 minutes, and you put the 45 minutes underneath the 15. 15 gallons in 45 minutes, and you've got the ratio set up of how fast you're using fuel. And now to find out how much fuel you're using per hour, All you have to do now is look around the flight computer until you find 60 minutes on the inner scale. 60 minutes for an hour, and when you find 60 minutes on the inner scale, the outside scale will tell you how many gallons you would use in a full hour and how many gallons would you use in an hour. You'd use 20 gallons in an hour, so what you're burning is 20 gallons per hour. 20 gallons per hour. See, nothing to it. And there really isn't anything to it as long as you keep the rules on using the computer in mind. And remember, if you have any problem with a computer, you can do it all with a pencil and paper. It's supposed to make things easier for you. If it doesn't make things easier for you, don't worry about it. Just use a pencil and paper or an electronic calculator instead. Now, the other thing we use in figuring our cross-country planning is a plotter. And there are a couple of things that you need to watch out for, four mistakes or problems actually, that you need to watch out for using the plotter. First of all, if you're an old-timer, had that plotter for a while, and if you've left it sitting on the glare shield in your aircraft out at the airport, it gets pretty darn hot in there, and if that plotter has gotten really hot, it will actually shrink and warp. Now, you say, I can mash it down, no problem with that, and measure off on the paper. Sure, you can mash it down, but the warping is not the problem as much as the shrinking is. If it's really gotten hot, the plotter can actually end up an inch or an inch and a half shorter than it should be. And that makes it awfully difficult to come out with a correct distance. So measure your plotter against someone else's or measure it against a mileage scale on a chart and see if your plotter is really the length it should be. The second thing to watch out for on a plotter is the 0 point is not at the end. Now, when you're used to using rulers and yardsticks, that kind of blows your mind because 0 is at the end there. But on a plotter, 0 is not the end. On a plotter, the 0 point is in somewhat from the end. So make sure when you're measuring distances using the plotter that you actually start from the 0 point on the plotter, not from the physical end of the plotter itself. The third thing to watch out for on the plotter that can trap you if you're not careful is there's two different mileage scales on that side of the plotter. Nautical miles and also statute miles. On this plotter, nautical miles on the outside scale and statute miles on the inner scale. Sometimes you'll need to measure distances in nautical miles, sometimes you'll need to measure it in statute miles, but make sure you read the questions very carefully and then you choose the proper scale. The fourth potential problem is sectional versus world aeronautical chart. The side of the plotter we're looking at is the sectional chart scale, and those are the kind of charts that we're going to be working with. But the other side of this plotter has a scale for a world aeronautic chart, and on the world aeronautical chart, the same physical distance will give you twice as many miles. And so you're not going to come out with the right answer if you're using the wrong side of the plotter. So make sure that you're using the proper side. Let's recap the four things you need to watch out for as far as using the plotter are concerned. First of all, make sure that yours has not shrunk and warped, particularly that it's not shrunk, that the physical length of it is the correct length. Measure against somebody else's or against a mileage scale on a chart. Be careful because 0 is not at the physical end of the plotter. It's in a little bit from there, and make sure you measure from the actual 0 point, not the physical end. Check and see whether you need to measure in nautical miles or statute miles, and make sure you pick the correct scale. And on the written exam, you're going to be working with a sectional chart scale, but whether in real life, make sure whether you're using a sectional or world aeronautic chart, and make sure that you're on the proper side of the plotter so that you're using the proper scale for the kind of chart you're actually using. Keeping those things in mind, and you won't have any problem with a plotter at all. Now, let's figure out some information about a trip, and to do that, let's go to the FAA figure pages, figure 14. Now make sure that you're on figure 14 and not page 14. Go to the FAA figure pages in the middle of the course book to figure 14. Now, where the trip is going to start is in the upper left-hand corner of that page. The upper left corner of that page is Hampton Roads Airport. And from Hampton Roads Airport, the trip is going to be down to the southeast. You cross over Chesapeake Municipal Airport. I don't know where they came up with that name, but Chesapeake is what it is. And from there you continue on down into the southeast, and where you end up is in the lower right-hand corner of the chart down at First Flight Airport. First Flight Airport, which is at Kitty Hawk, where all this flying stuff began in the first place. Okay, that's the route of flight that we're going to be flying. Let's go back up to Hampton Roads Airport in the upper left-hand corner, because the FAA will tell you that you cross Hampton Roads Airport at 14:56, that you then cross Chesapeake Airport at 15:01, and the question is, what time will you arrive at First Flight Airport down at Kitty Hawk? First thing we want to do is figure out how many minutes it took us to fly between these two airports. We crossed Hampton Roads, they tell us, at 14:56, and we crossed Chesapeake at 15:01. So how many minutes is it between those two airports? 5 minutes. It took us 5 minutes to fly between the two. What we need to know now is how many miles it is between them, and that will give us our ratio on how fast we're flying. So what we do is we take our plotter and we slide it onto this chart, put it along our course line. The 0 point on the plotter goes on Hampton Roads Airport. Make sure you're at the 0 point, not the physical end of the plotter, and then measure from there down. Now make sure that you're on the sectional chart side of your plotter and look at the nautical miles scale. We're going to work all of this in nautical miles. Look at the nautical miles scale and come down to Chesapeake Airport, and you can read on your plotter right there how many miles that is, and it's 10 miles from Hampton Roads down to Chesapeake Airport. Okay, that's the information we need for the first part of the trip to figure out how fast we're flying. But while we're here, let's go ahead and measure and find out how many miles we've got left to go. So put the 0 point now down on Chesapeake Airport, and with the 0 point down on Chesapeake Airport, then we're going to go all the way down to First Flight Airport down in the lower right-hand corner and take a look and see how many miles it is from Chesapeake down to First Flight. And when you get it down there and slide it around, you should come up with a mileage right at 49 miles. Should come up with 49 miles between Chesapeake and First Flight Airport. Okay, 10 miles between Hampton Roads and Chesapeake, 49 nautical miles from Chesapeake on down into First Flight Airport. The next thing we want to do is go to the circular slide rule side of the computer. And when you get to the circular slide rule side of the computer, what's the first thing you always put on that side of the computer? How fast? How fast goes first? And you say, well, gee, I don't know how fast I'm going. But sure you do, because you know that you covered 10 nautical miles in 5 minutes. So all you have to do is set up that ratio on the flight computer. So look on the outside scale and find the 10. 10 for 10 miles. And you know that you covered it in 5 minutes. So move the inner dial around and put the 50, which represents 5 minutes. We're going to use the 50 because we don't have a 5 as such on the inner dial. Use the 50 for 5 minutes next to the 10 for 10 miles on the outside scale. Now we've got our ratio set up of how fast we're flying. To find out how many nautical miles an hour we're covering, what our speed is, you simply look around the inner scale until you find the 60. 60 minutes or an hour on the inner scale, and on the outside scale you find that we would cover 120 miles, nautical miles, in 60 minutes. The 12 represents 120 nautical miles in 60 minutes. So we're making a speed of 120 knots, 120 nautical miles an hour. Alrighty, we know what speed we're flying now. We've got that ratio set up on the flight computer. We measured the distance on the second leg, and what did that distance come out to? 49 nautical miles. So don't move anything, don't rotate the dials, just simply look around the outside scale of the flight computer. Mileage is always on the outside scale. Find 49 on the outside scale, miles are on the outside, and when you find 49 on the outside scale, the next scale in will tell you how many minutes it's going to take you to fly for 49 miles, and I come up with 24, 25, looks like 24 and a half minutes. So it's going to take 24 and a half minutes to finish that trip on in to First Flight Airport. Now, to find out what time you're going to arrive at First Flight Airport, what you do is you add the 24 and a half minutes to your time over the second fix, your time over Chesapeake Airport. And what time did we say you crossed Chesapeake Airport at? 15:01. 15:01, and add your time en route to, from there down to First Flight of 24 and a half minutes, and you should get to First Flight Airport at 15:25.5. Now, a couple of things that people are very prone to do, mistakes, when they're working this kind of problem. One of them is they tend to add the time to the first time check and not the second one. The second time check, the one over your second fix, is the one that you add the time that you compute to. So you add it to the 15:01 in this case. The other mistake that people tend to make is they tend to measure the distance on the second leg from the first airport, Hampton Roads, instead of from the second airport, Chesapeake. You've already measured the distance from Hampton Roads when you got the 10 miles from there to Chesapeake. So you measure your distance from the second fix, Chesapeake, and add the time to the time over that second fix, which in this case was 15:01. Okay, you got this down, nothing to it. Let's do another. Take a look on figure 17. Go back a little bit further in the book to figure 17. And when you get to figure 17, take a look in the upper left-hand corner. The upper left-hand corner is where we're going to start out. This is a trip on Victor 185, which starts in the upper left corner. It's the blue line going down there. We've enhanced it with some red arrows to help you find it. And you're going to take a trip to the southeast on Victor 185. Now, the FAA will tell you that you cross the 248 radial off of the ALLLLL VOR. That VOR is up here off in the upper right corner. You cross that radial at 9:51. As you fly on to the southeast, you cross the next radial, the 216-degree radial, still off of ALLLLL, at 10 o'clock. And you continue on down to the southeast, and where you're going to end up is down at the Savannah Vortex. Right down here in the southeast part of the chart, the lower right corner, you're going to end up at the Savannah Vortex. And the question is, what is your estimated time of arrival at the Savannah Vortex? Okay, to work that, we do it the same way that we did the last question. We go to our first fix, which was the 248 radial of the ALLLLL VOR. We cross that first fix, the 248 radial of the ALLLLL VOR, at 9:51, and we cross the second radial at 10 o'clock. So what we need to do to find out how fast we're traveling is measure the distance between them. So whip out your plotter, lay it down there on that chart. Make sure you use the 0 point and not the physical end of the plotter, and put it over where the 248 radial crosses your course line. And measure from there down to where the 216-degree radial crosses your course line. And you'll come up there with a distance of, here's 10, here's 15. You come up with a distance of 11 nautical miles. You're going to come up with a distance of 11 nautical miles. Okay, we've got a distance of 11 nautical miles on that leg. The next thing we want to figure out before we leave the chart here is how many miles is it. Oh, by the way, before we look away from here, we crossed the first fix at 9:51 and the second fix at 10 o'clock. How much time did it take us to fly between those 2 points? 9 minutes. From 9:51 to 10 o'clock is a time of 9 minutes. So we know that we did 11 miles here in 9 minutes. let's measure the remaining distance and make sure how far we've got to go. So we put the 0 point of the plotter on the 216-degree radial, and then we look all the way down in the lower right-hand corner of that chart down to the Savannah Vortex. And when we get down to the Savannah Vortex, and we've got this line going across to mark it, you'll come up with a mileage, a distance of 40 nautical miles. Okay, so we've got 40 nautical miles to go on the second part of the trip. Whip out your trusty old computer, go over to the circular slide rule side, and the first thing you always put on the circular slide rule side is what? How fast? How fast are you traveling? Well, you're traveling 11 nautical miles in 9 minutes. So set that ratio up on your flight computer. Look on the outside scale until you find the 11 for 11 nautical miles, and then move the inner scale around until the 90, which represents 9 minutes, because we don't have a 9, use the 90 to represent 9 minutes, is next to the 11 on the outside scale. And you've set up your ratio there of doing 11 nautical miles in 9 minutes. Now, to find out how fast you're doing, how many knots, how many nautical miles an hour, you simply look around the inner scale until you find the 60. When you find 60 minutes on the inner scale, the outside scale will tell you how fast you're traveling. And it looks like we're doing 70, 71, 2, 3, looks like about 73 and a half knots. Okay, we've got 73 and a half knots here. That's our speed. We measured the distance for the second part of the trip as 40 nautical miles. Don't move anything, just simply look around the outside scale of the computer, because distance is always on the outside scale, until you find 40 miles. And when you find 40 miles on the outside scale of the computer, the next scale in will tell you how many minutes it's going to take to travel that distance. And what we come up with is 30, 31, 32, this is 33, well, if you were going to do it to the nearest half minute, it looks like about 32 and a half minutes. Looks like about 32 and a half minutes. Now, you add that time to the time over the second checkpoint, not the first checkpoint, but the second checkpoint, and here's what your times end up looking like. You cross the second checkpoint at 10 o'clock. It's going to take you 32 and a half minutes to cover the remaining distance down to the Savannah Vortex. So what time are you going to get to the Savannah Vortex? Is 10:32.5, 10:32.5. So remember to measure your distance from the second checkpoint, not the first, and add your time, the 32 and a half minutes, to the second fix, and not to the time at the second fix, and not to the time over the first fix. Otherwise, you're going to come up with the wrong information. Now, the other thing that you can use your flight computer for, in addition to figuring out time and distance, is you can use it to solve wind problems, and we're going to do that in just a minute. The wind, of course, is going to affect your flight. It will increase or decrease your speed, and you can use the wind side of the flight computer in order to determine your ground speed and in order to figure out what your crab angle is going to be, how the nose of the airplane has to be pointed to compensate for the wind. So before we actually start working anything on the wind side of the flight computer, let's talk about some definitions of terms. Define some terms so you and I agree on what we're talking about. First of all, your course is your path of flight over the ground. The course that you're flying is your path of flight over the ground. Now, your course can be defined relative to either true north or magnetic north. True course is your course reference to the true north pole, reference to true north, and you obtain it by reference to latitude and longitude lines. Magnetic course is your course reference to magnetic north as opposed to true north. Now, the true north pole, the geographic north pole, is different than the magnetic north pole. Magnetic north pole is located up in northern Canada, and there in some parts of the country there's quite a bit of difference between them. The difference between true course and magnetic course is due to magnetic variation. Magnetic variation is the difference between the true North Pole and the magnetic North Pole, and you find magnetic variation by looking on the red dashed isogonic lines on the sectional and world aeronautical charts. From true course to get to magnetic course, you have to compensate for this magnetic variation. Now, to get your magnetic course, there's a couple of ways to do it. One of them is you can actually measure off of a compass rose around a VOR or vortex, because remember those compass roses are aligned with magnetic north, and so that would give you a magnetic course. Or you can measure a true course, find the magnetic variation from the isogonic lines on the chart, apply it to your course, and that will give you a magnetic course. Depends on what happens to be easier for exactly what you're doing. Now, your heading is the direction that the nose of the aircraft is actually pointed. The direction the nose of the aircraft is pointed, and that can be relative to either true north or magnetic north. If you take your course and you adjust for the wind correction angle, that will give you your heading. The wind is blowing from one side or another, and in order to keep from being pushed off the course that you want to fly, you actually have to crab the nose of the aircraft one direction or another, depending on which direction the wind is from. So the wind correction angle is the reason for the difference between your course and your heading. And when you adjust your course, your path of flight over the ground, for the wind correction angle, you get your heading, and the heading is the way the nose of the airplane is actually pointing. And you can be referencing these either to true north or to magnetic north. So you could have a true course resulting in a true heading, or a magnetic course resulting in a magnetic heading, depending on how you started. Now, your wind is what gives you the difference between the course and the heading. And your wind, when you're flying, is always given to you in true direction, except for takeoff or landing. Your runways are lined up with magnetic directions, and therefore for takeoff and landing, they give you the wind relative to magnetic. But for in-flight computations, the wind is always given to you relative to true direction, and that's going to be the easiest way in general to work with things. So let's assume that we ended up with a magnetic heading, the direction that the nose of the airplane is pointed, reference to magnetic north. How do we get from magnetic heading to the heading we're actually going to put in the glass of our magnetic compass in the airplane? The compass heading is sometimes, but not always, the same as the magnetic heading that we want to fly. And the reason for the difference is deviation. Deviation is the error that the magnetic compass has due to magnetic fields in the aircraft. It's not only affected, the compass is, by the magnetic fields of the Earth, but it's also affected by magnetic fields in the aircraft, and that is called deviation. So you would like to fly a certain magnetic heading, but in order to actually fly that, you may have to put a slightly different number in the glass of the compass in order to get where you want to go. And the reason for the difference is the deviation due to magnetic fields in the aircraft. And we're going to look at it in a little bit. But there would be in the aircraft, or maybe on the panel, a compass correction card. And what that compass correction card would do is it will say to you, for a particular magnetic heading that you want to fly, this is what you actually have to put in the glass of the compass in order to get where you're trying to get. The compass correction card. Now, your true airspeed is the speed of the aircraft through the air. But when we're trying to get somewhere, we have to measure our speed over the ground. So the ground speed is the speed of the aircraft over the ground, and the difference between the true airspeed and the ground speed is due to, guess what? It's due to the wind. Sometimes the wind will speed us up, sometimes the wind will slow us down, but the difference between, or the reason for a difference between our true airspeed and our ground speed is going to be whatever wind we have that we're working with that particular flight. Now, let's talk about how we would measure magnetic course. The FAA has a number of questions on the test where they will ask you, how do you measure your magnetic course? And there are a couple of ways to do it. One of them, the very easy way, is to simply use the compass rose of a VOR or Vortac and directly measure what that course is. So take a look on figure 13. Take a look on figure 13, and we want to take a look at the sectional chart on figure 13. Make sure you're on figure 13, not page 13, and start in the upper right-hand corner of that page. And in the upper right-hand corner, we've got McVille Airport. Up in the upper right, area A, we've got McVille Airport. And the FAA will say to you that you're on a flight from McVille Airport going southwest, and where you're going to is Jamestown Airport. And Jamestown Airport is located right here in the center of the Omni Rose, and Jamestown VOR happens to be located right on the Jamestown Airport. Okay, you're coming down from McVille Airport down to Jamestown Airport. What you would do if you wanted to use the compass rose of the VOR or Vortac in order to measure that is you would pick up your plotter, and you would put your plotter down on that chart, and you would put the straight edge on McVille Airport, which is now off our chart up in the top here, and just simply run that plotter down so that you've got a straight line between McVille Airport and Jamestown Airport. And then you would look and see where that plotter crosses the compass rose. And remember, the compass rose is oriented to magnetic north, so by getting a course this way, we're going to get a magnetic course. Now, the problem is that the part of our course line that crosses the compass rose coming down into Jamestown, if we read the course off of the top part of the compass rose, here is 0, this is 10 degrees, it would be about 13 degrees. But a course of 013 degrees or 13 degrees would have you going northbound, north-northeast bound, rather than coming southwest bound. And so instead of reading off the top part of the compass rose, what you would do is simply extend that line straight on through down to the bottom part of the compass rose, and you would read the course off the bottom part. And why are you reading it off of the other side? You're reading it there because that's the direction that you're flying. You're flying basically south-southwest, so that's the direction on the compass rose you need to read. And here's 180, here's 190, so it looks to me like the magnetic course here is 193 degrees. Simple, easy way to find your magnetic course. Now, how else can you find your magnetic course? Another way that you can find your magnetic course is to use the lines of latitude and longitude to measure your true course and then convert it to magnetic course. And let's take a look at how we would do that. Take a look at figure 18. Now make sure you're on figure 18, not page 18, and when you get to figure 18, take a look in the lower left-hand corner of that page, down roughly in area A, but in the lower left-hand corner is Air Park East Airport. And let's assume that you're on a flight from there going pretty much eastbound, and where you're going to is over to Winnsboro Airport over in area B. And here's Winnsboro Airport over here. That's your trip. Now, you are headed basically eastbound, but what you need to do is measure your course, your true course, in order to find out exactly what direction you are indeed headed. Now, before you use your plotter to measure that course, let's take a look at the plotter and define a couple of parts of the plotter. The bottom straight edge is what we've been using to measure with before. I call that the bottom straight edge. The top part of the plotter, where it runs, connects to this protractor area here, is what I call the top straight edge of the plotter. And that top straight edge of the plotter is what we're going to be using when we put it on the chart in order to measure our true course. Okay, when you look at the chart, what you need to do is put the plotter down so that that top straight edge is lined up along your course. And we've drawn our course here in red here. Now, you're going to slide the plotter along your course line until the center grommet in the center is on either a line of longitude, as it is here, and we've darkened that in nice and heavy so that it shows up real well, or depending on how your course is oriented, you could use a line of latitude also. Doesn't make any difference, just simply whichever one crosses your course line. So you put the top straight edge of the plotter lined up along your course line, and you slide it along your course line as you need to until the grommet, which is that little hole in the center of the protractor area along the top straight edge, until that little grommet is lined up not only on your course line, but also on a line of latitude or longitude. In this particular case, it's lined up on a line of longitude. And then all you have to do is follow that line of longitude up and select the proper scale. Now notice that we've got 4 scales here on the plotter. This is why before we ever started it, I said to you, okay, what direction roughly are you flying? And we decided that we were flying roughly eastbound. So when you follow that on up, the very outer scale on the courses is for basically headed eastbound, and here is 80 degrees. Now here is something that's interesting about figuring out what your true course is. This is 80, but off to the right over here is 70, and further off over here is 60. So the numbers are actually going backwards of the way you would expect them to go. Normally, you expect to see bigger value numbers as you go around to the right. In this case, you're getting bigger value numbers as you go around to the left. So on this easterly scale, here's 80, and then to the left of it is east or 90. So if you are 2 tick marks to the left of the 80, which is where our line of longitude goes up, that is 82 degrees. And that can be tricky. And if you read it as 78 degrees instead, which it is not, but it's what you'd kind of expect to see there, then you're going to come up with a wrong answer. Okay, 80 and 2 tick marks gives us a true course of 82 degrees. We've got a true course. But what the FAA wants to know is a magnetic course. And what is the difference between the true course and the magnetic course? Magnetic variation, the difference between the true North Pole, the geographic North Pole, and the magnetic North Pole, which is located up in northern Canada. So we need to know the magnetic variation. And to find the magnetic variation, we look for the red dashed isogonic line. Okay, we're looking for the red dashed isogonic line running along our course line, and we find it here at 6 degrees 30 minutes east. So we've got 6 degrees and 30 minutes of easterly magnetic variation. Okay, that's very nice. Let's call that, by the way, as we're figuring it here, it's 6.5, so let's call it 7. 7 degrees east variation. We know what our variation is, 7 degrees east, but what do we do with it now that we've got it? Well, here's a memory saying that will help you keep straight whether you add it or subtract it. East is least and west is best. East is least, so you subtract easterly magnetic variation, and west is best, so you add westerly magnetic variation. East is least, west is best. So we started out with a true course of 82 degrees. We subtract the 7 degrees east variation, and we come up with a magnetic course of how much? 0.75 degrees. We measured the true course on the chart using the plotter and the line of longitude, 82 degrees. We found the magnetic variation line, the isogonic line, 6.5, we'll call it 7 degrees east, easterly, so we subtract it, and that gives us a magnetic course there of 75 degrees. See, nothing to it. And there really isn't, as long as you look at the problem beforehand and you say to yourself, okay, roughly which way am I going? Make sure that you understand, in this particular case, that you're going from Air Park East to Winnsboro and not the other direction. A lot of people get confused by that if they don't read the problem carefully. So just make sure you read the problems carefully and you rough out in your mind ahead of time roughly what direction you're headed, so that when you come up with an answer, you can check it for reasonableness. Now, the steps that we go through when solving a wind problem, when we get over to the wind side of the flight computer, are this. First of all of the headings, courses, and wind have to be expressed the same relative to direction. They all have to be true, or they all have to be magnetic. Headings, courses, and winds have to be expressed the same. The easiest way to start is with true course and work through the wind first, and the reason that's the easiest way to start is because your winds aloft given to you for en route flight planning are always given to you relative to what direction? True direction. So if you measure a true course on the chart, then you've got true winds that Flight Service gave to you, and you can work with those first before you have to worry about variation. Makes it a little bit easier, a little bit less work. So here's how we work through a problem. You measure your true course off of the chart. Using your wind, you figure out what your wind correction angle is, and that gives you a true heading. Your true course is your actual path of flight over the ground. Your wind correction angle is the amount of crab to the left or right you have to hold to compensate for the wind trying to push you off course, and that will give you your true heading being the direction the nose of the airplane is actually pointed. And so far, we're all still expressed relative to true north. Okay, you take your true heading and you apply the magnetic variation. East or west variation. East is least, subtract easterly variation. West is best, you add the westerly variation. You get that from the red dashed isogonic lines on the chart, and that will give you your magnetic heading. How the nose of the airplane is pointed relative to magnetic north as opposed to true north. You take the magnetic heading, which is the heading you want to fly, and then you apply the compass deviation in order to come up with your compass heading. Deviation is the correction because of errors in the compass due to the magnetic fields in the aircraft itself. And the compass heading tells you what you're actually going to have to put in the glass of the magnetic compass in order to fly the heading that you want to fly and get to your destination airport. Okay, let's put all of this into play, and to do that, let's take a look at Figure 17. Now on Figure 17, let's start up on the top, a little bit to the right of the center, roughly area alpha at ALLLLL Airport. And we've drawn a red line on our chart here going down to the southwest. We're going to take a trip from ALLLLL Airport down to Claxton Evans County Airport, roughly in Area B, down in the lower left-hand corner of the chart. Okay, that's the trip that we're going to take. The FAA is going to give us our wind and airspeed information, and they're going to ask us to find out what our compass heading will be and what the estimated time en route is going to be. Alrighty, the first thing we need to know is what our wind is going to be, and our wind is from 090 degrees, 90 degrees at 16 knots. Okay, 90 degrees is basically from the east. We're flying basically a southwesterly course. If we have an east wind, it's going to come in and it's going to be pushing at us like this. Okay, we've got a wind from the east. What that's going to do, it's a little bit of a tailwind, so it's going to speed us up a little bit. You can see that it's going to give us a little bit of a push, although not much. And because it's going to try and push us off course to the west, we're going to have to crab a little bit to the east in order to compensate for it, a little bit to the left. So just by looking at it on the chart and knowing that the wind is from the east and we're flying southwest, we know already that we're going to have a little bit of a tailwind, which means that our ground speed should be a little bit faster than our true airspeed, and also that we're going to have to crab a little bit to the left, that we should have a left wind correction angle as we're flying along. Very important to just get some general orientation done that way, so that if you come up with a number later on, you aren't uptight about, or you've got a good basis to figure out whether it's a reasonable number. Always remember to look at things and say, does it make sense? So put your plotter down on the chart and move this upper straight edge so that it's lined up with your course line. And then slide the plotter along your course line so the grommet in the center of the protractor area along the upper straight edge is lined up not only with your course line going to the southwest here, but also with this line of longitude. And we've darkened this line of longitude so that it shows up real well for you. Now, again, remember, you've got 4 scales here. You've got south, north, west, and east, and we're going southwest bound. We're going southwest bound, so we're going to pick up the westerly scale, and if you follow the line of longitude up until it goes through this westerly scale, the second one in, here's 210, 220 is to the left, so the numbers get bigger as you're going around to the left, which is the reverse of the way they're normally going to be. So our course is 210, 11, 12, 213 degrees. We have measured off a true course of 213 degrees. Okay, we've got our true course of 213 degrees. What we want to do now is go over to the wind side of your flight computer, the clear plastic disc side of the flight computer. And let's get some terminology straight before we start working with it. First of all, up at the top is the true index. Underneath the true index, we're going to put the true wind direction, and later on we're going to put our true course that we just measured. This hole down in the center of the clear plastic disc area is the grommet, and we will find our ground speed down under there when we're done with our problem. Think of the G's as going together. The G for ground speed, G for grommet, those are going to go together. Now notice that on this, underneath the clear plastic disc, you've got wind strength arcs, 80, 90, 100, 110, 120, and so on. That's what you should be seeing on this side of the flight computer. If instead you're looking at wind strength arcs down here that start at about 200 or 250 and go on up to 600, you've got the jet airplane side of the wind side in there, and what you would need to do is take the slide out, turn it around, and put it back in again. What you want to have is wind strength arcs going from about 80 or 90 down at the bottom up to about 200 or so up at the top. And if you've had the flight computer apart for any reason, it's not uncommon for it to get put back together backwards. Okay, let's start in working our problem. We are on the wind side of the flight computer, so what do you suppose is the first thing we're going to put in on the wind side of the flight computer? The wind, of course, you guessed it, and as you remember, the wind is from 090 degrees at 16 knots. So what you do is you rotate this compass rose until 090 degrees, rotate the clear plastic disc until 90 degrees is underneath the true index up at the top. Okay, with 90 degrees underneath the true index at the top, look down in the center until you find the grommet in the center of that clear plastic disc. Now we want to mark the wind strength velocity up from that center grommet. And to do that, it's easiest if you put it on a handy starting reference point. The slide does not go all the way down to 0, so let's use 100 as a handy starting reference point. Move that inner slide until the center grommet hole is sitting on the arc for 100. Now, we're just doing that to have a handy reference point. We could have used anything as the reference point. This is just a very easy one to use. Now the wind velocity is 16 knots. So what we want to do is count up from 100 to 116. Okay, here's 100, 110. Here's 12, 14. Now each one of these is 1, not 2. That's a mistake you've got to watch out for, because in some parts of the flight computer, each one of these lines will represent a unit of 1, and in some areas they represent a unit of 2. Okay, so here's 110, 11, 12, 13, 14, 15, 116 right here. So you want to put your wind X at 116 on the flight computer. What you're doing is marking the wind direction and the wind velocity on the wind side of the flight computer. And if you draw an arrow between the Windex you put there and the center grommet, what it will do is visually represent the wind as we continue with the problem. Okay, we measured our true course off of the chart, and we got a true course of 213 degrees. So rotate that clear plastic disc until 213 is underneath the index up at the top. And when you have 213 underneath the index up at the top, the next step we're going to do is we're going to work with our true airspeed. Now, the FAA will give you the true airspeed in the problem, and your true airspeed in this particular case is 90 knots. Your true airspeed is 90 knots. Go back now to the center part of the clear plastic disc, and what we want to do is move that inner slide so the X for the wind is sitting on the 90 arc for our true airspeed. On the arc for 90 knots, our true airspeed. So move the inner slide so the pencil X that we put on there for the wind is sitting on the arc for our true airspeed of 90. Once you've done that, you can visually see what the wind is doing to our airplane. What we're doing is flying, going up this main center line here, that dark line. And here's the wind coming in from the left side and slightly behind us. So you can visually see that it's a tailwind, that our ground speed's going to be a little bit faster than our true airspeed, and you can also see that we're going to have to crab to the left in order to compensate for that wind. Okay, the ground speed and the grommet go together, so look underneath the grommet in the center of that clear plastic disc, and it's sitting on the arc for our ground speed. Here's 90 knots, here's 100 knots, so it looks like about 98 knots for our ground speed. Our ground speed is 98 knots, a little bit faster than our true airspeed. Where the pencil X for the wind is, to the left or to the right, in this case it's to the left, represents how many degrees we have to crab to compensate for that wind. Now this can be a tricky thing, figuring out how many degrees it is, because in this part of the flight computer, each one of these nearly vertical lines represents 2 degrees. Here's 10 degrees, here's 0, and there's 1, 2, 3, 4, 5 lines between them, so each of those lines is 2 degrees. But in other parts of the flight computer, each one of those nearly vertical lines will represent 1 degree instead. So make sure that you've counted on your part of the flight computer that you're working on, and you know for sure how many degrees each one of those nearly vertical lines is. Okay, in this case, each one of them represents 2 degrees, 2, 4, 6, 8, not quite 10. Let's call it 9 degrees left wind correction angle. 9 degrees of left wind correction angle. Okay, that's nice, but if we're working from our true course to our true heading, are we going to add that or are we going to subtract it? The easy way to tell is to look at the top of the wind side of the flight computer, and when you get up to the top, there's our true course of 213 degrees. And if you look around to the left, do the numbers get bigger or smaller as you go to the left? They get smaller value numbers, and so a wind correction angle to the left is going to give you a smaller value. You're going to subtract it. 213 minus a 9 degree left wind correction angle gives you a true heading of 204 degrees. We took our true course of 213, we adjusted for our crab due to the wind, and we come up with a true heading, which is the way the nose of the airplane is pointed relative to true north, of 204 degrees. But we want to know our heading relative to magnetic north, because that's what we need in order to fly, information relative to magnetic north. For that, we need to know how much variation we've got in the area, and for that, we go back to the chart. So we go back to the chart and we take a look at our course line and we look for a red dashed isogonic line, and sure enough, we find one, and on that red dashed isogonic line, it says 3 degrees west. We have 3 degrees of westerly variation. Now with westerly variation, are you going to add it or subtract it? Add it. East is least, subtract easterly variation. West is best, add westerly variation. We had a true heading of 204 degrees. We add 3 degrees westerly variation, and we get a magnetic heading of 207 degrees. But we're not done yet, because what we need to know is our compass heading, and for that we need to know how much deviation we've got on this general heading that we're flying. Look at the bottom of this chart, and down at the bottom of this chart you'll find the compass deviation card, the compass correction card, and it tells you if you want to fly a particular magnetic heading, this is the compass heading you have to fly. Now, one of the tricky things about the written exam is that this compass correction card, the FAA will not specifically refer you to it. It'll be down there at the bottom of the chart, but you've got to remember that you need to refer to it if they ask you for the compass heading that you're flying. In real life, of course, in the airplane, it'll either be on the compass or it'll be on the panel, but for the written exam, it's down at the bottom of the chart. Okay, we're flying a magnetic heading of 207 degrees. If you look on the bottom line of this compass correction card, here we've got south. If we wanted to fly a magnetic heading of south, which is 180 degrees, we would fly a compass heading of 181 degrees. So that is a correction of +1 in that area. The next magnetic heading they give us is 210 degrees, and if we wanted to fly a magnetic heading of 210 degrees, the compass heading we would actually have to steer, put in the glass of the compass, would be 214 degrees. That's a correction of +4. Well, 207 is a lot closer to 210 than it is to 180, so let's use a correction factor of +4. We're going to use a correction factor of +4 for the deviation, and that will give us a compass heading of 211 degrees. Okay, let's recap how we got from our true course to our compass heading. We started out by measuring on the chart, using the line of longitude, a true course of 213 degrees. Using the wind side of the flight computer, we figured we had a 9-degree left wind correction angle. A wind correction angle to the left will be subtracted, and that gave us a true heading of 204 degrees. To get our magnetic variation, we looked at the chart, the sectional chart, and found the isogonic line. It said 3 degrees west. West is best, so we add the 3 degrees westerly variation, and that gave us a magnetic heading of 207 degrees. We then looked at the compass correction card. We got the deviation. The deviation was +4 degrees. We added that to our magnetic heading, and we came up with a compass heading of 211 degrees. Okay, we've got a compass heading of 211 degrees. That's half the answer, but we also want to know our estimated time en route. To get our estimated time en route, we need to know how much distance we're flying. So let's take a look at the chart again, and let's put our plotter down and measure off that distance between Claxton-Evans County and going up to Allendale County Airport. We want to measure the distance using the plotter. And when you look along your plotter and measure the distance there, you're going to come up with a distance of 57 nautical miles. 57 nautical miles. Now make sure that you're using the sectional side of the chart, not the World Aeronautical Chart side, and make sure you start from the 0 point, not from the physical end of the plotter. 57 nautical miles. Okay, we know our distance, we know our ground speed, which was 98 knots. Now let's go to the circular slide rule side of the flight computer, and let's figure out how much time it's going to take us. And when you get to the circular slide rule side of the flight computer, what's the first thing you always put on it? How fast? How fast are we going? 98 nautical miles an hour. So find 98 on the outside scale. Distance is always on the outside scale, and move the inner dial around until 60 minutes is next to 98 on the outside scale. We've set up our speed by setting a ratio in the computer, a ratio of 98 miles every 60 minutes. Now, we're not going to fly for 60 minutes. We're only going to fly a distance of 57 miles. So look on the outside scale of the computer and find 57 miles. 55, 56, 57 miles on the outside scale of the computer, and on the inner scale you'll find how many minutes it's going to take you, and it comes up to how much? It comes up to 35 minutes. But we're not done yet, because in the question the FAA throws some information at us about our time in the climb, and the FAA says that we need to add some time. We need to add time in climb of an additional 2 minutes. So we figured out on the flight computer that it was going to take us 35 minutes to actually travel the distance, but we have to add how much for the climb? 2 minutes for the climb, and that will give us a total estimated time en route of how many minutes? A total estimated time en route of 37 minutes. 35 minutes for the trip plus 2 minutes for the climb gives us a total estimated time en route of 37 minutes. And see, nothing to it. And really, you've got it cold. There isn't anything to it. Just remember to take it slow, and as you get different figures, look at it and say, does it make sense? Too easy for you. Too easy for you. Let's do another problem. Let's take a look at figure 16. Let's take a look at the chart on figure 16. Remember, you don't want page 16, you want figure 16. And when you get to the chart on figure 16, where you're going is from St. Mary's Airport, area D, down in the lower left area of that chart. And we're going to be flying northwest from there, or north-northwest, up to Priest River Airport, which is very roughly area A. When the FAA puts these letters on here, they're not pinning the airports down real close. It's a very approximate area. But basically, we're headed north-northwest up to Priest River Airport. And the FAA wants to know our magnetic heading and our estimated time en route. Okay, first thing we want to do is draw a line on the chart from our departure airport, which is St. Mary's, up here to Priest River Airport. And then we want to take a look at the wind information the FAA gives us. And the FAA says that our wind is from 300 degrees at 14 knots. Okay, from 300 degrees at 14 knots. That means that the wind is coming in basically from the northwest. We're flying north-northwest, but the wind is coming down from the northwest. Is that going to be, visually looking at it, a little bit of a headwind or a tailwind? Which one? A little bit of a headwind coming down at us like this. Okay, and which way are we going to have to crab to correct for the wind? If the wind's coming in from 300 degrees, are we going to crab to the right or to the left? We're going to crab to the left. So we already know a lot about our wind and how our results should work out when we work it on the flight computer. First thing we need to do is pick up our plotter and measure our true course. Now when you put your plotter down, put the upper straight edge of the plotter along your course line so that it's angled up towards the top of the chart. I've darkened this line of latitude. We're going to use a line of latitude here instead of longitude. Doesn't make any difference, just whatever happens to cross your course line. Slide that plotter up until the grommet in the center of the top straight edge is both lined up on your course and also lined up right over the top of the line, in this case, of latitude. Now, again, remember, we have 4 scales, south, north, west, and east. In this particular case, we're headed northwest bound. We're headed basically north-northwest. And so as we come up through here and we look at the numbers on the scales, we're going to use the scale for north because that's basically the direction that we're headed. We're not really headed due west. We're headed almost north. Okay, and we look at where the line of latitude comes through the scale for north. Here's 340 degrees, 350 degrees. Notice again that the numbers are getting larger value numbers as you go around to the left, as you're moving up to the top here. So here's 340, and if you read these tick marks, it comes out right about exactly on 345 degrees. So we get a true course by measuring off of a line of latitude, a true course of 345 degrees, 345 degrees. Okay, now that we've got our true course figured out, what we want to do is go over to the wind side of the flight computer. And when you get on the wind side of the flight computer, what do you suppose is the first thing you want to put on it? The wind! Boy, you've really got it down. Okay, the wind is from 300 degrees, so rotate the clear plastic disc until 300 degrees is underneath the true index up at the top. 300 degrees is our wind direction. The wind velocity is 14 knots. The easiest way to mark the wind velocity is to go to the center of that clear plastic disc and put the grommet on 100 as a handy starting reference point. You can use anything as a starting reference point, but 100 is the easiest to keep track of since they don't have 0 on the slide. So put the center grommet on 100. The wind velocity is 14 knots. So mark up from 100 to 114 and put an X on there. When you get to 114, put an X and then draw a wind arrow coming down from the wind X to the center grommet. And that represents visually what the wind is going to be doing, the wind direction and velocity. Okay, now that we've got the wind marked on there, the next thing we want to do is look back at the top on the wind side and set in our true course. And we just measured our true course on the chart as 345 degrees. So we move that clear plastic disc around until 345 degrees is underneath our true index. Once we've got our true course, 345, set under the index, we look back at the center of the clear plastic disc. And when we look at the center of the clear plastic disc, that X, which represents our wind, we want to put it on our true airspeed. So we need to know what our true airspeed is. And when we take a look at the information they give us, our true airspeed turns out again to be 90 knots. Okay, our true airspeed is 90 knots. So we put this X for the wind, move the inner slide so the X for the wind sits on our true airspeed, the arc for our true airspeed, which is 90 knots. With the wind X sitting on the arc for 90 knots, you can visually see what the wind is doing to you. This arrow represents the wind, and we can see that the wind is a headwind. It will slow us down, and we can also see that we need to crab to the left in order to compensate for the wind. And that's exactly what we figured out when we looked at the chart and just kind of roughly drew in the wind relative to our course. Helps a lot on keeping us oriented. Okay, when we look under the grommet, the G's go together for ground speed and grommet. We read our ground speed under the grommet, and what do you get for a ground speed? You got it, 80 knots. We got a ground speed of 80 knots. Okay, now how much crab have we got for the wind? Count how many nearly vertical lines that X is to the left of the center and figure out what the value of those lines is. Because in this area, each of the nearly vertical lines represents 2 degrees of wind correction angle. So here's 2, 4, 6 degrees of left wind correction angle. 6 degrees of left wind correction angle. Are we going to add it or are we going to subtract it? Look at the top of the wind side of the flight computer, and when you look at the top, if you move around the compass rose to the left, do you get bigger value or smaller value numbers? Which one? Smaller value numbers. So with a wind correction angle to the left, are you going to add it or subtract it? Subtract it because you get smaller value numbers as you go around to the left. True course of 345 minus a 6-degree left wind correction angle gives you a true heading of 339 degrees, the way the nose of the airplane is pointed relative to true north. But you need to know how to point the nose relative to magnetic north, and for that you need the variation. And the place where you get the variation is you go back to what? That's right, the sectional chart. And what are you looking for? You're looking for the isogonic line, that red dashed isogonic line that gives you the magnetic variation. And just before we get to Priest River, there's the red dashed isogonic line running across our course, and we've got a magnetic variation of how many degrees? 20 degrees to the east. 20 degrees to the east. Well, are we going to add it or subtract it? Which one? Subtract it. East is least, so we subtract easterly variation, and that gives us a magnetic heading of 319 degrees. Now, on this particular question, they did not ask for the compass heading. They wanted the magnetic heading. And be very careful when you read the question what it is the FAA is asking you to give them. Very easy to get confused and make assumptions, and you don't want to make assumptions. That's dangerous on a written exam. So let's recap how we got to our magnetic heading. We started with a true course of 345 degrees, our path of flight over the ground, measured on the chart using the line, in this case, of latitude. We worked a wind problem and found out that we had a 6-degree left wind correction angle. Left wind correction angle we subtract to get a true heading of 339 degrees. That's the way the nose of the airplane will be pointed relative to true north. We then looked at the isogonic line on the sectional chart, the red dashed isogonic line, for our magnetic variation, and we got an easterly variation of 20 degrees. East is least, so we subtract that, and that gives us a magnetic heading, the way the nose of the airplane is pointed relative to magnetic north, of 319 degrees. Okay, all we have to figure out now is how long is it going to take us to get there? What is our estimated time en route? So the first thing we need to know to do that is we need to know how many miles we've got to fly. We take a look at the chart, we take a look at the route we've drawn on there between our airports, and we put the plotter down and we measure the distance off. And we measure the distance off, and when you get your plotter on there, remember to put the 0 point on the airport, not the physical end of the plotter. And when you look at the distance on there, you'll come up with a distance of 53 nautical miles. The distance here is 51, 2, 3. The distance comes out to 53 nautical miles. So we know how many miles we're going to fly, and we figured out earlier on the wind side of the computer that we're making a ground speed of 80 knots. So let's go to the circular slide rule side of the flight computer and figure out how long it's going to take us. And when you get to the circular slide rule of the flight computer, what's the first thing you always put on there? How fast. And how fast are we going? We're going 80 knots. So set that in a ratio. Look on the outside scale of the flight computer and find 80 knots. Move the inner scale until the 60 minutes is underneath the 80 knots. We're setting our speed in by setting a ratio in. A ratio of 80 nautical miles in 60 minutes. Okay, we're going to fly for 53 nautical miles. Distance is found on which scale of the computer? The outside scale. So look around the outside scale of the computer until you find 53 miles, 51 to 53 miles, and the inner scale will tell you how many minutes it's going to take you to fly 53 miles, and I come up with pretty close to 40 minutes, But you're not done yet, because the FAA is going to throw in the question information some information about how long you spend time in climb, and that's going to have to be added in. So we take a look at the information that they give us, and the time in climb that the FAA tells us in this particular question is 3 minutes. They tell us to add 3 minutes. Okay, when we worked it through on the flight computer, we came up with 40 minutes for our estimated time en route. We added 3 minutes time to climb, and that gives us a total estimated time en route of how many minutes? 43 minutes. Total estimated time en route of 43 minutes. And you guys have got it down cold. You are really doing super. And don't worry, you will enjoy it. You're going to have no problems at all doing your cross-country planning. Well, it's time to talk about everybody's favorite late-night reading material. You guessed it, the Federal Aviation Regulations. And the first thing we want to cover is the documents that you have to have on your person as a pilot in order to be able to fly. The first thing you need to have is an appropriate pilot certificate. A pilot certificate appropriate to the category and class of aircraft you're going to be flying. And we're going to talk about category and class a little bit later on. That's one thing you need on your person when you fly. The second thing you need on your person when you fly is a current medical certificate. A current medical certificate. Now that medical certificate and that pilot's license you do have to have on your person. It's a violation of the regulations if you don't have it when you're flying. And you can get a violation if a FAA inspector does a ramp check of you and you have been flying and don't have those on you. So make sure you are carrying them. Now, what class of medical certificate do you have to have? Well, there's 3 classes of medical certificate, and a private pilot can have either one of them, a first class, a second class, or a third class medical certificate. Let's talk about a first class medical certificate first of all. A first-class medical certificate is the kind of certificate that you have to have if you're going to be the captain of a scheduled airliner. And a first-class medical certificate is valid until the end of the 6th calendar month as far as first-class operations are required. Operations that require a first-class medical, mainly being the captain of a scheduled airliner. Valid to the end of the 6th calendar month after issuance. After those 6 months, then it downgrades and it becomes a second-class medical certificate. So let's talk about a second-class medical certificate. A second-class medical certificate is the class of medical that you have to operate as a commercial pilot. If you're going to fly for hire, give flight instruction, that type of thing, you need a second-class medical certificate. And a second-class medical certificate is valid until the end of the 12th calendar month after original issuance. And at that point, it then downgrades and it becomes a third-class medical. So you see, everything just keeps moving down. The first class, after 6 months, downgrades to a second class. The second class, after 12 calendar months, downgrades to a third-class medical. Now, a third-class medical is all that a private pilot has to have. He can have a higher class medical if he wants, but a third class medical is all that a private pilot has to have. And the third class medical is good for longer than the other two. The third class medical is good until the end of the 24th calendar month. So the third class medical is good for 24 calendar months after the original issuance. And a private pilot can have either a first, a second, or a third class medical certificate. Now, here's what the FAA is going to ask you on the written exam. First of all, they're going to say to you that you went out just to see if you could get one and got a first-class medical certificate. And that first-class medical certificate was issued on October 21st of this year. And what they want to know is, when will it expire as far as private pilot operations are concerned? Well, as far as private pilot operations are concerned, even though it's a first-class medical that you got, it's going to be valid for private operations for the same length of time that the third-class medical would be, which is how many months? 24 calendar months. So the first-class medical issued on October 21st, as far as private operations are concerned, will expire on the last day of October, October 30th, 2 years later. It's good for 24 calendar months. It expires on October 30th, 2 years later. So it doesn't matter which class of medical you've been issued. If you're operating as a private pilot, they're going to be good for 24 calendar months. So the FAA comes along. They haven't given up yet. You know them. They've got a lot of stamina. And they say to you, this time you got a second class medical certificate. And your second class medical certificate was issued on July 15th. And for private operations, they ask you, what time is it going to expire? When is it going to expire for private operations? Okay, regardless of the class of medical, if you're operating as a private operation, not commercial, not airline operations, How long is it good for? 24 calendar months. And when does it expire? Same day of the month or last day of the month? The last day of the month, so it will expire on July 31st, at midnight on July 31st, 2 years later. And finally, they get around to giving you the typical example, which is that you go out and get a third-class medical certificate, which is all you have to have as a private pilot, as a private operator. And that third-class medical certificate was issued to you on May 3rd. And the question is, for private operations, when will that third-class medical certificate expire? Okay, the third-class medical is valid for how many months? 24 calendar months. And does it expire on the same day or last day of the month? Which one? Last day of the month is 24 calendar months, and it's 2 years later, 24 months later, so the certificate issued on May 3rd expires on the last day of May, May 31st, 24 months or 2 years later for private operations. So no matter which class of medical you get, it's going to be valid to the end of that month, 24 calendar months later. Takes care of your medical without any problem. Now, your pilot certificate is only valid for the category and class of aircraft for which the pilot is rated. And let's talk about what we mean by category and class. The whole great big ball of wax of aircraft, everything that flies, is subdivided into 4 categories. That's our big subdivisions. Categories are rotorcraft, airplanes, lighter than air, and glider. Rotorcraft includes helicopters and gyroplanes. Airplanes, the category of airplanes, includes our fixed-wing powered aircraft. The category of lighter than air is balloons, blimps, things like that. And the 4th category is gliders. Now, that has divided aircraft into 4 categories, but that's not enough division, really. So categories are further divided into classes. So classes are a subdivision under category. For instance, under the category of rotorcraft, we've got class of helicopters, we've got the class of gyroplanes. Under the category of airplanes, we've got multi-engine land, we've got single-engine land, we've also got single-engine sea, multi-engine sea. So those are the classes under the category of airplanes. Under the category of lighter than air, we've got balloons, we've got airships like the Goodyear blimp. So the class is a subdivision under category. Now, a subdivision under class is the type of aircraft. Type refers to make and model. And make and model can be something very basic like a Cessna 172 or a Cherokee 140, or it can be on larger aircraft. For instance, a Citation, a Cessna Citation CE-500, or some other aircraft. So type is a subclassification under class. Sometimes you have to be rated for a particular type of aircraft, and it actually goes on your pilot's license, and we'll talk about when that's required later on. But to kind of recap the progression from category to class to type, here's what it looks up like. You start off with all aircraft, and then you break it down into categories. You've got the categories of airplane, rotorcraft, lighter than air, and we don't include it here, but you've also got the category of gliders. Under categories, you subdivide it into classes. For instance, under airplanes, we're showing the class of multi-engine land. You have additional classes under the category of airplanes of single-engine land, single-engine sea, multi-engine sea, and so on. Under rotorcraft, one of the classes is helicopters. You also have a class of gyroplanes. Under lighter than air, one of the classes is airship. You've also got a class of balloons, various kinds of balloons. You take classes and you subdivide them into type. And remember, type means make and model. So one type of multi-engine land airplane is a Cessna 340. One type of a helicopter, which is in the category of rotorcraft, one type of helicopter is a Hughes 500. One type of airship is the Goodyear blimp. So the movement is from category, the big subdivision, to class, which is subdivisions under category, into type, which is the actual make and model of aircraft. Now, some aircraft require that the pilot in command have a type rating in order to fly it. And a type rating simply means that you get a checkout in that specific make and model of aircraft. And they put right there on your license that you can fly that make and model of aircraft. A type rating, you need to know for the written exam, is required if you're going to be a pilot in command of a turbojet-powered airplane. In other words, not a turboprop, but one with pure jet engines on it, a turbojet-powered airplane. A type rating is also required, by the way, this is just for your personal information, if you're going to fly a heavy aircraft, which is one weighing more than 12,500 pounds. But what they ask you about on the test is, when is a type rating required to be pilot in command? And the answer they're looking for on the test is, if you're going to be pilot in command of a turbojet-powered airplane, a jet airplane, you need a type rating, a checkout in that actual make and model in order to act as pilot in command. Okay, we figured out what you need on your person in order to be legal to fly. The airplane, the aircraft, also has some documents that it has to have in order to be legal to fly. And the first one we're going to talk about is the airworthiness certificate or special flight permit. The airworthiness certificate, think of it like a birth certificate, because it comes with the airplane when it comes from the factory, and it has to be displayed at the cabin or cockpit entrance so that it's legible to the passengers or crew members. The airworthiness certificate remains valid as long as the aircraft is maintained and operated in accordance with the regulations. Now, the airworthiness certificate, what do you have to do with the airworthiness certificate? It has to be displayed at the entrance to the cabin or cockpit so that it's legible to the passengers or the crew members. And it does not expire. It remains valid as long as you maintain and operate the aircraft according to the regulations. Okay, what else does the aircraft have to have? Well, it needs a registration certificate, and the registration certificate shows the owner of the aircraft, lists whoever the owner of the aircraft is, and the registration certificate has to be current so the FAA can find the owners. If there's any hazards, airworthiness directives that have to be issued, any way the FAA needs to get a hold of the owners, they need to know who the current owners are, so you've got to have a current registration certificate. Now, what else do you have to have? You also have to have the operating limits of the aircraft in the aircraft. And the operating limitations are found in a number of different places. The operating limitations are found in the airplane flight manual. It's also found in markings and placards inside the aircraft, or any combination of those. So it could be in the flight manual, it could be in markings, it could be in placards like this, but whatever the limitations of the aircraft are, in this particular case they're talking about gear speeds, maximum speeds on the aircraft to operate the gear and fly with gear down and so on. These kinds of placards constitute operating limitations, and they all have to be in the aircraft one way or another. Could be markings and placards, could be a flight manual, any way that gets it done. Now, there are some restrictions on what you can do depending on what kind of aircraft you're flying. For instance, aircraft, in terms of operating them, are divided into some categories, and one category is a restricted category aircraft. A restricted category aircraft is like a crop duster. A restricted category aircraft is an aircraft designed for a particular work operation, and the FAA does not want it to be flown for other purposes. Well, I don't know what you do with a crop duster anyway, but they don't want you out carrying passengers for hire and stuff like that in a crop duster, so they restrict the use in a restricted category aircraft to the certain kind of work operations that it was built to do. If you're operating a restricted category aircraft, such as a crop duster, flight over a densely populated area is normally prohibited. In other words, it's built for a specific work operation, and normally in a restricted category aircraft, you cannot fly normally over a densely populated area. Okay, suppose that's not the kind of aircraft you're flying, but suppose you're flying an experimental category aircraft instead. You're flying an experimental category aircraft, which is basically a home built. If you're flying an experimental category aircraft, you cannot operate an aircraft with an experimental certificate in a congested airway. The FAA is basically saying that aircraft built for certain purposes, or ones that are built by a home builder as opposed to a factory, we don't want to endanger anybody on the ground. And so the aircraft with an experimental certificate cannot be operated in a what kind of airway? In a congested airway. Okay? Suppose that you're a private pilot, got your license recently, and you would like to go out and be pilot in command of an aircraft that does glider tows. Takes people like this upstairs in order to be able to do their aerobatic act with a glider or any other kind of glider work. If you want to act as pilot in command of an aircraft towing a glider, there are some limitations on you. First of all, if you only have a private pilot certificate, you need 100 hours of pilot flight time in powered aircraft. As a private pilot, you can tow a glider, but you must have 100 hours in powered aircraft in your logbook if you're going to be doing it. They want to make sure that you've got enough pilot flight time, that you've got some experience before you start towing a glider. Now, the 100 hours is if you are a private pilot. Suppose you've got a commercial license. Well, you don't have to worry about the 100 hours anymore, because when you get your commercial license, you're going to have a lot more than that. But for anybody to act as pilot in command of an aircraft towing a glider, you have to have had, within the preceding 12 months, 3 actual or simulated glider tows while accompanied by a qualified pilot. So for anybody, whether you've got a private license, commercial license, whatever, you cannot tow a glider unless you've made how many glider tows? 3 actual or simulated glider tows in the last how many months? 12 months. And you have to be accompanied by who? A qualified pilot. Does it have to be a flight instructor? No, does not have to be a flight instructor. I didn't say it had to be a flight instructor, but you do have to be accompanied by a qualified pilot when you make those 3 glider tows. And by the way, those 3 glider tows can be actual or simulated, but you need 3 of them in the last how many months? In the last 12 months. Now, let's assume that you want to be pilot in command of a high-performance airplane. If you're going to be pilot in command of a high-performance airplane, something like this Mooney, for instance, you have to have received flight instruction from an authorized flight instructor who then endorses your logbook. So if you're going to act as pilot in command of a high-performance aircraft, you have to have gotten what? Flight instruction, and the flight instructor has to do what to your logbook? He has to actually endorse your logbook that he has given you that instruction in a high-performance airplane. Now, there are 2 separate and distinct definitions of a high-performance airplane. The first definition of a high-performance airplane is an airplane that has, like the Mooney, retractable landing gear, flaps, and a controllable propeller. If it's got all 3 of those things, it doesn't make any difference how much horsepower it's got. If it's got retractable landing gear, if it's got a controllable propeller, if it's got flaps, doesn't make any difference how much horsepower the engine's got. It's a high-performance airplane, and you're going to need flight instruction and a logbook endorsement in it. The other definition of a high-performance airplane is an airplane that has more than 200 horsepower, more than 200 horsepower. And it's quite possible that you could end up flying an airplane that has more than 200 horsepower but does not have retractable landing gear. For instance, you could be flying this Cessna 195. This Cessna 195 has a 300 horsepower engine, or at least that's the size that they usually put in it, but it does not have retractable gear. Nonetheless, that qualifies as a high-performance airplane. So if you want to act as pilot in command of an airplane that has more than 200 horsepower, you've got to get flight instruction in an airplane that has more than 200 horsepower. If you got flight instruction in an airplane that had retractable gear, flaps, and a controllable propeller but did not happen to have more than 200 horsepower, that doesn't do it for you. To fly an airplane, be pilot in command of an airplane with more than 200 horsepower, you need that flight instruction in an airplane that does have more than 200 horsepower. Okay, let's talk about your private pilot privileges. In general, as a private pilot, in general, you cannot charge for your flying. In general, the general rule is that you cannot accept any money for your flying, but there are a couple of exceptions. First of all, a private pilot can share the operating expenses of a flight. He can share the operating expenses of a flight with his passengers. And the second thing a private pilot can do is he can participate in a charitable airlift. In other words, if you have a charity function going on, and part of that charitable function is that you take people up and you give them a ride, and they don't pay you, but they make a donation to the charitable organization, a private pilot can do that. And it's an interesting thing, the way the FAA phrases it on the test, because the FAA says you can carry passengers who pay for the flight if a donation is made to a charitable organization for the flight, which is rather an awkward way of saying that the payment that they're making for the flight is really going to the charitable organization. It is not going to you. So the private pilot can share the operating expenses of a flight, and he can carry passengers who are making a donation to a charitable organization, basically a charity airlift. But other than that, the general rule is that a private pilot cannot charge for his flying. Now, let's talk about your recency checks and experience, what you need to act as pilot in command and to be current and legal as far as the regulations are concerned. First of all, to act as pilot in command, and this applies to anybody, you need a logbook endorsement within the last 24 months that shows accomplishment of a flight review or a pilot proficiency check. So every 24 months, you have to either do a flight review with a flight instructor, or you have to have a pilot proficiency check. Doing something like getting a new rating or something like that would count as this flight review or proficiency check. And you need that within the last how many months? 24 calendar months. This, by the way, is what we pilots usually call a biennial flight review, but the FAA calls it simply a flight review on the written exam, a flight review or proficiency check. Okay, you're legal to be pilot in command because you've got that flight review in the last how many months? 24 calendar months. But now, you want to carry passengers with you. You don't want to fly solo. You want to carry passengers with you. If you're going to carry passengers, here's what you have to have done. You need to have made 3 takeoffs and landings in the last 90 days in the same category and class of aircraft you're going to be carrying passengers in. Now remember, if we're working with airplanes, the category is airplanes. In this case, the class is going to be single-engine land, could be multi-engine land. That's the single-engine versus multi-engine, land versus sea makes the class distinction. So you need 3 takeoffs and landings in the last 90 days in the same category and class of airplane. If you're going to carry passengers in a single-engine land airplane, like a Cessna 172, you need to have made those takeoffs and landings in the same class, a single-engine land airplane. It does not have to be exactly the same type. If you do your takeoffs and landings in a Cessna 150, that's fine as far as a Cessna 172 is concerned. That's fine as far as a Cessna 210 is concerned, as long as it's a single-engine land airplane. If you want to carry passengers in a twin-engine airplane, a multi-engine and land airplane, then you need to do your takeoffs and landings in a multi-engine land airplane, whatever is the same category and class you're going to be flying. So you need how many takeoffs and landings? You need 3 takeoffs and landings. You need them within the last how many days? Last 90 days, and they have to be in the same category and what? Class. Does it have to be in the same type? No, it does not have to be in the same type. Okay, you've gone out and you've done your takeoffs and landings in a Cessna 150. But now you've got some friends who would like to go up in a tailwheel airplane. What do you do if you want to carry passengers in a tailwheel airplane? Something a little bit special. Your takeoffs and landings have to have been made in a tailwheel airplane to a full stop. I guess the FAA figures it's a little bit harder, and it truly is, to get a tailwheel airplane stopped with the tail still behind the nose where it belongs. And they want to make sure you can do it before you carry passengers with you. So to carry passengers in a tailwheel airplane, the takeoffs and landings have to have been done in what kind of airplane? A tailwheel airplane, and they have to have been done how? To a full stop. Touch and go is not allowed. They've got to be done to a full stop. Okay, you can carry passengers in a single-engine land airplane, and now you got yourself qualified to carry them also in a tailwheel airplane. But what if you want to carry passengers at night? If you're going to carry passengers at night, the optical illusions on landing are a little bit trickier at night than in the daytime. So if you're going to carry passengers at night, the 3 takeoffs and landings have to have been done at night, and again, they have to be done to a full stop. So to carry passengers at night, your takeoffs and landings have to have been done when? At night, and they have to have been made how? Touch and go or full stop? Full stop for the night takeoffs and landings. Okay, night landings and takeoffs, by the way, those 3 takeoffs and landings will count for daytime as well as nighttime. So if you go out and do your 3 takeoffs and landings full stop at night, that will make you current to carry passengers at night and in the daytime both. Now, what is the definition of nighttime? This is interesting. For the purpose of carrying passengers, night, for the purpose of carrying passengers, is the period from 1 hour after sunset to 1 hour before sunrise. 1 hour after sunset to 1 hour before sunrise is nighttime for the purpose of carrying passengers. So the FAA is going to come along and give you a question on the test like this. You are not current to carry passengers at night. And what they say, the way they say that is, your recency of experience requirements are not met as far as carrying passengers at night. So you're not current to carry passengers at night. Official sunset is at 18:30, and they want to know the latest time passengers may be carried. Well, if sunset is at 18:30, how much time do you have after sunset before it's night for the purpose of carrying passengers? You have 1 hour, and that means the latest time you can carry passengers would be what time then? 19:30. 1 hour after sunset is the last time to carry passengers at night if you have not met your recency of experience requirements. So the definition of night for carrying passengers is 1 hour after sunset to 1 hour before sunrise. But that is not the official definition of nighttime as far as the rest of the regulations are concerned. So let's take a look at the rest of the story as far as nighttime is concerned. The official definition of nighttime is from the end of evening civil twilight to the beginning of morning civil twilight. I'm not exactly sure what use that's going to be to you, except I do know it'll give you a question on the written exam. So the definition of nighttime, the official definition for general purpose in the regulation, is from the end of what? Evening civil twilight to the beginning of what? Morning civil twilight. Very useful to know. Okay, you, as the pilot in command of an aircraft, you need to know that you are the final authority as far as the operation of the aircraft is concerned. Nobody else really knows what's going on in the aircraft. Nobody else is in a position to make the final decision as to what you need to do if you have some kind of problem. So as the final authority on the operation of the aircraft, if you have an in-flight emergency that requires immediate action, you can deviate from the regulations to whatever extent you need to in order to meet the emergency. So you can deviate from the regulations if you have an in-flight emergency to the extent you need to in order to meet the emergency. You do not have to make a written report about that unless it is requested. No written report is required, even if you deviate from the regulations, unless they specifically request a written report. So, as pilot in command of an aircraft, if you have an in-flight emergency requiring immediate action, do you have the authority to deviate from the FARs? Yes, you do. You can deviate from the regulations to the extent necessary to meet the emergency. If you do that, do you have to make a written report? No, not unless they specifically request it. And only if they request it do you give them a written report. Now let's talk about some pre-flight planning. Before every flight that you take, there's certain pre-flight planning, pre-flight action that you have to take. And that pre-flight action that you have to take includes, among other things, for every flight, becoming familiar with all available information about the flight and determining the runway lengths at the airports that you're going to use. That is before every flight, regardless of the weather conditions, regardless of how long the trip is going to be, miles or time. You have to, among other things, become available with all available information about the flight and determine the runway lengths at the airports that you intend to use. Now, suppose that you're on a flight that is not in the vicinity of an airport. Some of the things you have to do for a flight not in the vicinity of an airport, you have to have, among other things, an alternate course of action. Just in case things don't work out the way that you intend them to, you have to have an alternate course of action in case the flight cannot be completed as planned. What else do you have to do? For a flight not in the vicinity of an aircraft, you also have to check the weather, you have to check the fuel requirements, and you have to be familiar with known traffic delays. Known traffic delays are things like going into Indianapolis when the Indy 500 is on. There's no way ahead of time there's really going to be some traffic delays, and they can tell you all about it. A flight, by the way, not in the vicinity of an airport, one definition that I've heard from some FAA people is that if you are within power-off gliding distance of an airport, then you're in the vicinity. And if you're not within power-off gliding distance, then you're not in the vicinity of the airport, and all of this pre-flight action is going to need to be taken. Okay, one of the things we said you have to do as part of that pre-flight is check your fuel requirements. There are some fuel requirements for day and night VFR flight. First of all, logically enough, you got to have enough fuel to fly to your first point of intended landing. Or to put it another way, you got to have enough fuel to get where you're going. You got to have enough fuel to reach your intended destination. Now, what kind of reserve do you have to have? For day VFR flight, your fuel reserve is 30 minutes after you reach your destination. So you need enough after you reach your destination to fly for 30 minutes after that at normal cruising speed. Not at some super economical fuel setting, but 30 minutes at normal cruising speed. Now, what if you're flying in the night instead? For night VFR flight, the fuel reserves go up a little bit, and for night VFR flight, the fuel reserves go up to 45 minutes. After you reach your destination, you need a reserve of 45 minutes, and again, that is at normal cruising speed. Airports that are open with lights and so on them are a little bit harder to find at night, so they want you to have a little bit more fuel reserve just to make sure you don't put it down in some dark and lonely place because you ran out of fuel. Now, there is some maintenance that needs to be done on a regular basis on aircraft. The responsibility for determining whether an aircraft is in condition for safe flight is the responsibility of, you guessed it, the pilot in command. The pilot in command is the one with the last available chance, clear chance, to look that airplane over and see if it's airworthy and ready to fly. This particular airplane doesn't quite look ready to go yet. But the pilot in command is the one with a chance to walk around the airplane, look and see if a fuel truck's run into it or any other problem has come up that makes it not in a condition for safe flight. So the pilot in command is responsible for determining that. Now, who is responsible for seeing that the airplane is maintained properly? That is the responsibility of the owner or operator of the aircraft. So the responsibility to maintain it is truly the responsibility of the owner or operator, but the responsibility to make sure that it has been properly maintained and is currently airworthy is that of the pilot in command before he takes it up in the air. Now, all aircraft, unless they're on some other kind of special inspection procedure, have to be inspected every 12 calendar months. Think of it like a medical for the aircraft. And for the aircraft, the annual inspection is due every 12 calendar months, and it goes to the end of the 12th calendar month. So it goes to the last day of the month 12 months later. It's good through the end of the 12th calendar month. For instance, the FAA is going to give you a question on the test that looks like this. They're going to say to you that the last annual inspection was done on July 12th. And what they want to know is, when is the next annual inspection due? Well, does it expire on the same day or last day of the month? It expires on the last day of the month, and it expires how many months later? 12 months later. So it expires on the last day of July, July 31st, the next year, which is 12 months later. That's when the next annual is going to be due. Now, if the aircraft is used for certain purposes, the aircraft has to have 100-hour inspections. Now, 100-hour inspections are required among other times if the aircraft is a rental aircraft and used for flight instruction, or if passengers are carried for hire. So if it's a rental aircraft used for flight instruction, or if passengers are carried for hire in the aircraft, then it has to have 100-hour inspections. Now, this is in addition to the annual inspection. This is not a substitute for it. This is something more in addition that has to be done for the aircraft to make sure that it stays in good mechanical shape. Now, what if you happen to be 300 miles away from home base when the time comes up for that 100-hour inspection, when the hours come up and you need the 100-hour inspection? That 100-hour limit can be exceeded. You can go over it by not more than 10 hours. You can exceed it by 10 hours if necessary, no more than that, in order to reach a place where the inspection can be done. So what that would let you do is return the airplane back to the home base in order for the inspection to be done there. Now, what it does not let you do is keep on flying that airplane and use up all the time. The 100-hour limit can only be exceeded by the 10 hours in order to get the airplane back to a place where the inspection can then immediately be done. Now, that 10 hours is deducted from the 100 hours when if you exceed the limit by 10 hours, it's deducted from the next 100 hours for the next 100-hour inspection. Basically, the way it works out is if you go over the 100-hour limit by 2 hours, 5 hours, or the whole 10 hours, doesn't make any difference which, you do not get to keep having that extra time and just pushing the limit on ahead. The next 100-hour inspection will be due from when the previous 100-hour inspection was actually due, not from when it was actually done. So here's what the FAA will throw at you on the written exam. What they're going to say to you is, the 100-hour inspection on the aircraft was due at 3302.5, but you weren't in a place where you could get it done, so it took a little bit of flying to get it back to where the inspection could be done. And the 100-hour inspection was actually done at 3309.5. When, they will ask you on the test, is the next 100-hour inspection due? Well, the next 100-hour inspection, is it due 100 hours from when it was last actually done, or 100 hours from when it should have been done? 100 hours from when it should have been done. So the next 100-hour inspection will be due 100 hours after 3302.5. It will be due at 3402.5. When it was actually done is not relevant. What you get is 100 hours from exactly when that 100-hour inspection was due. You don't get to keep pushing it up by going over the 100 hours. It's due 100 hours from when it was last due, in this case 3402.5, and that is an inspection that you do in addition to the annual. It does not replace the annual. Okay, let's assume that you finished off an annual inspection. That has to be shown in the aircraft maintenance records. Now, the aircraft maintenance records is just a fancy name for saying the aircraft logbooks. And so the aircraft logbooks or the aircraft maintenance records will have to show that the annual inspection has been completed, the date of the annual inspection, and a return to service note. In other words, the mechanic says that I did this annual inspection on such and such a date, it is complete, and I certify this aircraft for return to service. So the maintenance record, the aircraft log, will show completion of the annual, the date of the annual, and show that it has been returned to service. Now, sometimes the FAA puts out airworthiness directives having to do with the mechanical condition of an aircraft. The airworthiness directives affect all kinds of different things. This particular one happens to be in regard to the aircraft engine, but sometimes it will have to do with things like rigging the ailerons, checking for potentially broken or worn parts, all kinds of different things, and they relate to the mechanical condition of the aircraft. When an airworthiness directive has put out, it is mandatory that it be complied with. The owner of the aircraft does not have a choice. The airworthiness directives are part of the regulations, and it is mandatory that you comply with them. So how do you show that you have indeed complied with an airworthiness directive? You put the information in the maintenance records. So where you keep the status, the information about the airworthiness directives that you've complied with, is in the maintenance records, which is a fancy name for what? The aircraft logbooks. The aircraft logbooks. Now, there is certain preventive maintenance that the pilot himself is able to do. The FAA defines preventive maintenance as being simple or preservation operations and the replacement of small standard parts that do not involve complex assembly operations. Now, to give you an itemized list of what you're going to run into on the written exam, let's talk first of all about some items the FAA does give you on the test that are preventive maintenance. Now, this is just a very small segment, a small listing. You can find the whole thing in the Federal Aviation Regulations Part 43, which has to do with maintenance on an aircraft, or you can simply ask your local FAA office. Items that you're going to run into on the test that are preventive maintenance are the servicing of the landing gear wheel bearings and refinishing of the decorative coating on the fuselage of the aircraft, but not on the tail or other control surfaces. Refinishing of the decorative coating of the fuselage only. I guess what they're talking about there is repainting it, and the pilot can repaint the fuselage, but he can't touch the control surfaces or any balance surfaces on the aircraft. Also, he can service the landing gear wheel bearings. Those are two things you're going to find on the written exam that the FAA says are preventive maintenance. Now, here are some things you're going to find on the written exam that are not preventive maintenance. Things that are not preventive maintenance are, for instance, alteration of the main seat support brackets in the aircraft. Another one that is not preventive maintenance is adjusting the engine, making engine adjustments to allow auto gas to be used in the aircraft. Changes in the aircraft empty weight. Any equipment that goes in or out of the aircraft that permanently changes the empty weight of the aircraft, that is not considered to be preventive maintenance. Removing and installing glider wings is not considered to be preventive maintenance unless there is an exception in the regulations that says if the glider wings were specifically designed for quick removal and quick installation by a pilot, then it would be preventive maintenance and the pilot can do it. But on the written exam, the question does not give you in the answers the complete spelling out of all of the quick assembly and disassembly information about the glider wing. So as far as the written exam is concerned, removing and reinstalling glider wings is not considered to be preventive maintenance because it doesn't go through all of the rigmarole that it needs to in the answer to properly qualify it as to when removing and installing glider wings does constitute preventive maintenance. So on the written exam, removing and reinstalling glider wings does not constitute preventive maintenance. Other things that are not preventive maintenance is repair of landing gear brace struts and repair of portions of the skin sheets by making additional seams. Those things, among many others listed in Part 43, are not preventive maintenance as far as the FAA is concerned. Okay, let's assume that you, the pilot, have gone out and done some preventive maintenance. What kind of record, if any, do you have to make of it? Well, you do indeed have to make a record. And where do you guess the record of the pilot's preventive maintenance work is going to go? In the aircraft logbook. It's going to go in the maintenance records for the aircraft. Now, what information needs to go there? The name of the person who did the work, and it has to be, and the description of the work he did, and it has to be entered in the maintenance records. In other words, the FAA says pretty logically that if people are going to go out and work on an airplane, even if they're just doing preventive maintenance, they want at least the name of the person who did the work and a description of what they did to be in the logbooks so that if there's any problem that develops later on, they know who to talk to about it.